Helicopters are the true flying machines. They can take off and land without the need for a runway. They can hover in the air. They can maneuver in any direction in a 360-degree space. This video will unveil the complexity and science behind flying a helicopter. After going through the physics behind the helicopter flying, you will also understand why helicopter pilots are doing an incredibly complex job. Helicopters use the airfoil principle to generate lift. When the blades rotate relative to the air, the special airfoil shape will generate lift force and make them fly. The blades derive rotation from an engine, more specifically, a turboshaft engine. The compressor sucks the air in and pressurizes it. Fuel is burned in this pressurized and hot air. The hot exhaust leaves the combustion chamber, passes through a series of turbine stages, and make them turn. There are two sets of turbines. One turbine set turns the compressor, and the other set turns the helicopter's rotor shaft. Jet engines of airplanes are used to generate thrust force. However, the primary function of the helicopter's jet engine is to turn the rotor shaft. The most challenging part in helicopter operation is its controls. That means, how can it fly forward? How can it fly backward? Sideward? Or how can it take a turn? The answer is quite simple. Just rotate the helicopter towards the direction you want to move and just fly. When the helicopter is at an angle, the force produced by the blade is not vertical. The horizontal component of this force will make the helicopter move in the desired direction. The vertical component of the blade force will balance the gravitational force. Now the real challenge is how to turn the helicopter in the desired way. To learn the science behind helicopter turning, we need to learn more about the airfoil principle. The lift produced by an airfoil varies with the angle of attack. Generally, the greater the angle of attack, the more the lift. Now think for a moment. What happens if the one blade were at one angle of attack and others were at a different angle? The lift forces acting on the blades will be different in this case. The variations in the lift forces will definitely result in a torque that can turn the helicopter. You can observe the beautiful blade motion required to achieve this non-uniform lift force distribution. It is clear that the blades must keep on changing angle of attack so that at one particular location, the angle of attack is always the same. Such complex motion of the blades is easily achieved by a swash plate mechanism. Let's get an exploded view and understand the basic components first. The bottom swash plate does not spin, but it can move and tilt as shown. A top swash plate is fitted on the bottom swash plate via a bearing. So the top swash plate can inherit all the motion of bottom swash plate while at the same time it can rotate independently. The top swash plate is attached to the rotor shaft with the help of a driver. So the top swash plate will always move with the blades. The blades are connected to the top swash plate with the help of control rods. The interesting thing about this arrangement is that just by tilting the bottom swash plate, we will be able to achieve the varying angle criterion of the blades. That means, with this swash plate tilt, we will always be able to maintain a positive angle of attack at the rear and a negative angle at the front portion of the rotor disc. In short, swash plate tilting backwards produces a torque as shown. This kind of control is known as cyclic pitch. Now back to the basic helicopter control. How will this torque affect the helicopter's motion? The most obvious answer is that the helicopter will turn forward and move as shown. Unfortunately, this answer is completely wrong. What happens in reality is the helicopter will turn sideward as shown. This is definitely a weird effect. By applying torque in one direction to a rotating object, the object turns in different direction. This effect is known as gyroscopic precession. Gyroscopic precession is not a new phenomenon of physics. If you carefully applied Newton's second law of motion to rotary objects, you will be able to predict this phenomenon. According to Newton's second law, force is the rate of change of linear momentum. Similarly, torque is rate of change of angular momentum. Let's consider this rotating blade. It will have an angular momentum as shown. Now, assume that the helicopter has tilted as shown due to some torque action. If you vectorially subtract the first angular momentum from the second, you can figure out the torque required for this operation. It is interesting to note that to turn the helicopter forward, the torque applied should be towards sidewards. That means to tilt the helicopter forward, the swash plate should tilt sidewards as shown. You can again verify from Newton's second law of motion that if you keep the front portion at negative angle of attack and the back portion at positive angle, the helicopter will simply turn sidewards. Gyroscopic precession is a truly intriguing phenomenon, but it conforms perfectly with Newton's second law of motion. If you just lift the bottom swash plate without tilting it, you can see how the angle of attack of all three blades will vary by the same amount. This means that the helicopter lift force will be the same in all three blades, and the helicopter can move up or down without any tilt. Such blade control is known as collective pitch.